Let's look at how derivatives can help us find properties of functions and how they behave. So we're going to look at terms that are increasing, decreasing, and concavity. We use the terms increasing and decreasing and constant to describe the behavior of functions, and I think this is fairly straightforward. We would say a function is increasing if it's moving up to the right. It would be decreasing if it's going down to the right. So here our function increases again on that interval. And then here we have an interval where the function is constant. That is, the y value is not increasing or decreasing. So very simply, as a definition, a function f is increasing on an interval if f of x1, that's your y value, is smaller than f of x2, that's the other y value, where x2 is greater than x1. So in other words, the y values are getting larger as we move to the right. And similarly, a function f is decreasing on an interval if f of x1, the y value, is greater than f of x2, where x1 is smaller than x2. In other words, your y values are getting smaller as we move to the right. And a function f is constant on an interval if f of x1, the y value, is equal to f of x2, the y value. So in other words, the y values are not changing over that interval. So what does the derivative, which we know is the slope of the tangent line, what does that tell us about the behavior of functions? Well, I've drawn one here, and we can see that this function increases to about this point right here, and then it decreases to this point about right here, and then it remains constant. Well, let's look at the slope of the tangent lines, and I'm just going to pick some points on here. And if we'd sketched some little tangent lines, they might look something like this. Whoop. Sorry, lost the graph there for a second. Now we got her back. Okay. So I put on here some imaginary tangent lines. And if we were to look at the slope of this line, this might have a slope of, just going to make this up, say about 3. Maybe this is a slope of 2. Maybe this is a slope of a half here. This is a slope of 0. Here our slope might be -1. Maybe here it's -2. This might be a slope of -4. That might be -1. That looks about -1/2. And this is slopes of 0. So if we were to split this graph up, so we said the graph was increasing over here. This is the increasing area. And then the graph seems to be decreasing in this area. And here our graph is constant. Well, look at the slopes. If you look at the slopes of the tangent lines for all of these places here where the graph is increasing, what do we notice? We notice that they are all positive. So if a function is increasing, then the slope of the tangent line, or f prime of x, has to be positive, greater than 0. These slopes are all positive. On this interval in here, we have an interval where the graph is decreasing. It's going down as we move to the right. When we look at the slopes of all those tangent lines, they are all negative. So a function is decreasing if f prime of x is less than 0, or the slope of the tangent line is negative. And if we look at the slopes of the tangent lines here where the graph is constant, we can see their slopes are 0. The slopes of the tangent line is 0. So f prime of x must equal 0. So increasing, the derivative will be greater than 0. Decreasing, the derivative will be less than 0. Constant, the derivative will equal 0. And that leads us to this theorem. Let f be a function that is continuous on a closed interval a to b. So continuous function, we had one right here. And we could close the interval off. We could actually end it. Instead of these arrows, we could end the graph right here. So we have a closed interval. And we can take the derivative on anywhere between a and b. Then, if the derivative is greater than 0 for every value of x, then the function would be increasing. And if the derivative is less than 0 or negative, then the function is decreasing. And if the derivative is equal to 0, right over here, for every value, then f is constant on that interval. Well, let's consider this example. Find the values of x where the function f of x equals 3x squared minus 7x plus 4 is increasing and where it's decreasing. Well, we know a function will be increasing where the f prime of x is greater than 0. And we know it'll be decreasing if f prime of x is less than 0. So we simply need to take the derivative here and determine what f prime of x is. So we would get 6x minus 7, taking the derivative of that function. And if we want to know where it's increasing, then we will let f prime of x, which is 6x minus 7, we will set that greater than 0. And solving this inequality, bringing the 7 over to the other side, and dividing by 6, we would get x is greater than 7/6. So this function is increasing on the interval of 7/6 to infinity. Notice back here in the definition that we would say if f prime of x is greater than 0 for every value on this open interval, then we say that f is increasing on the closed interval. So when we have increasing, we will have a square bracket, or another way of writing this, greater than or equal to 7/6. And similarly, finding out where it's decreasing, we would take the derivative, which is 6x minus 7, set it less than 0, and so the function is decreasing, we say, for x less than or equal to 7/6, or writing it this way, we would get that interval where the function is decreasing. Example 2. Again, find the values of x where this function is increasing and decreasing. Well, we know that we need to take the derivative, and doing so gives us 3x squared minus 4x minus 7. And we would like to find out where it's increasing. So we will take this function and figure out where is it greater than 0. Well, this is one that we would maybe try to factor, because we need to find out the solution to this quadratic inequality. So we could either factor it or we can use the quadratic formula. If we were factoring it, we would need to find two numbers that multiply to negative 21 and add to minus 4. And we can do that because those numbers are minus 7 and 3. So I'm going to just factor this. And we have a common factor of x here. We have a common factor of 1 here. And so we get 3x minus 7 and x plus 1. And we are trying to determine where this is greater than 0. So we would end up finding out where it's equal to 0. We know that if x equaled 7/3 or if x equaled minus 1, then this is where this inequality is equal to 0. So we could now plot these on a number line. And what I'm going to do now, since this is the places where it's equal to 0, then I'm going to test these three regions. And substituting in a number from region 1 on my number line, say minus 10, would make this term negative. 3 times negative 10 would be negative 30. Negative 30 minus 7 is negative 37. And negative 10 plus 1 is negative 9. But a negative times a negative would make a positive. So f prime of x, if we look at the derivative signs, is positive in this region. If we look at it between negative 1 and 7/3, say let's try 0, this term would be negative, this term would be positive. A negative times a positive is a negative. So f prime of x is negative in this area. And if we look at greater than 7/3, say a number like 10, this is positive, positive, positive. So where is f prime of x less than 0? On this region right here. And where is f prime of x greater than 0? Where is it positive? On this interval here, less than -1. So we'd say it's decreasing from -1 to negative infinity, and it is also increasing from 7/3 to positive infinity. So just summarizing, a function is increasing where the derivative is greater than 0, and a function is decreasing on the intervals where the derivative is less than 0. Another way in which we can define the behavior of a function is its concavity. Functions are said to be concave up if they hold water, and concave down if they were to spill water. And so if we look at this function here, we see that there is an area here where it seems to be able to hold water, and there's an area here that the bucket's upside down type thing. It would spill water. So there's a point right in here where the graph goes from being concave up on that interval, and it's concave down on that interval. Let's take a look though at the slopes of the tangent lines again. So again, let's put some points on here. And if we looked at these tangent lines, and I'm just going to change this point here to a green dot, because that seemed to be where our concavity changed. Let's look at these slopes. This one might be a slope of +4. Maybe here it's +2. Perhaps here it's 1. Maybe here it's 0. This might be -1. Maybe we're at -3 here. This looks to be about -1 again. 0, +1, +2. Maybe we're way up to +4 there. So those would be some plausible slopes of the tangent line on this function. Well, if we look at the slopes here, this is the point where our concavity changes from concave down to concave up. Watch what's happening to the slopes. 4, 2, 1, 0, -1, -3. The slopes of the tangent lines are all getting smaller. They're decreasing until we hit this point. Then the slopes of the tangent lines start to increase again. So if this is our concave, down region, we can say that the slopes of the tangent line is increasing. Sorry, no, 4, 2, 1, 0. Sorry, we're going down there. The slopes of the tangent lines are decreasing. The numbers are getting smaller. A function over here, which we know is concave up, when we look at the derivative, the slopes of the tangent lines are getting larger. Those slopes are increasing. Well, if we know that the slopes are actually decreasing on that interval, then what that means is the change in the slope, the change in the slopes of the tangent lines are decreasing. And if the change in the slopes are decreasing, then that means that if we took the derivative of the derivative, that should be less than 0. The second derivative is less than 0. And over here, since the rate of change of our slopes is increasing, then if we took the derivative of this derivative, we should find that the second derivative is greater than 0. That is, the change in the slope is increasing, is positive. So an analysis of the slopes of the tangent line show that if the derivative is increasing, that's what happened here, then the function is concave up. And if the derivative is decreasing, then the function is concave down. So this leads to the following theorem. If we have a function that is twice differentiable, in other words, you can take the derivative twice, then if the second derivative is greater than 0 on an interval, then the function f is concave up on that interval. And if the second derivative is less than 0 on the interval, then f is concave down on that interval. Now we have one other definition to talk about. If f, a function f, is continuous on an open interval and it has a point x naught, and if f changes concavity at that point x naught, then that point is called an inflection point. So in other words, the place where the derivative changes from concave up to concave down, or concave down to concave up, then we call those points inflection points. So let's just analyze all our definitions now. Here's a function, and on this graph we need to label the areas where it's increasing, decreasing, concave up, concave down, and inflection points. And I'm going to use the red pen for the areas where it's increasing and decreasing. So on this interval here, the graph is going down. We would say this is a decreasing interval. Then the graph goes up from here to here. We now have an increasing interval. And then the function is going down, 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 down. We have a decreasing interval. So decreasing, increasing, decreasing. Now we need to talk about concavity, so let's use the green pen for that. So the areas where it's concave up, where it's concave down, and inflection points. I'm going to find the inflection point first. So that's the area where it changes from concave up to concave down, and it looks like it's right about here. So this would be our inflection point. And on this interval here, it is concave up. And on this interval over here, it is concave down. So if we were analyzing the derivatives on this interval, the second derivative would be less than 0 and concave up. So in this area here, the second derivative would be greater than 0. And in this interval here where it's decreasing, the first derivative would be less than 0. The first derivative less than 0. And in this area where it's increasing, the first derivative would be greater than 0. So the first derivative tells you where it's decreasing or increasing. The second derivative will tell you where it's concave up or where it's concave down. So let's look at a function and analyze it entirely. Where is it concave up, concave down, and any inflection points? So I'm going to take the first derivative here. I would get 12 minus 3x squared. And I'm going to take the second derivative, and it would be negative 6x. So I want to find out where is the first derivative greater than 0. Where is f prime of x, which is this? Where is it greater than 0? Well, that would give us negative 3x squared is greater than 12, negative 12, bringing the 12 over to the other side, dividing by negative 3. Remember, when we multiply or divide by a negative, we got to change the inequality sign. So we would get positive 4. And I'm now actually going to find out where is it equal to 4, so I can do this all at once. And of course, that's when x is plus or minus 2. So on my number line, I'm going to do a test of the first derivative. Find out where is it positive, where is it negative. So if I were to try a point like negative 5, negative 5 squared is 25. 25 is not less than 4, so this is a negative region. Or you could test the point back up in here. Negative 5 squared, 25. 25 times 3 is 75. 12 minus 75 is a negative number. Then I'm going to test 0. Putting in 0 for x gives me 0. This is going to be a positive. 12 minus 0 is positive. And testing another point in here, such as 10, would give us back to a negative number when we evaluate the first derivative. So we can say that the function now is increasing on the interval from negative 2, and it is decreasing for x values less than or equal to minus 2 or x greater than or equal to positive 2. So there's the increasing and the decreasing. Now looking at the concavity, I need to work with my second derivative. So where is the second derivative equal to 0? This would be our inflection point. So negative 6x equals 0, divide by negative 6, and of course we get x equals 0. So here is our inflection point. It has an x value of 0. If I want to get the y value, I simply put it back into the function and we would get a y value of 5. So the inflection point is at 0, 5. Now testing the second derivative sign, if I try a number like minus 5, negative 6 times negative 5 would be positive 30. So we have a positive second derivative here. And looking at a number greater than 0, such as 5, negative 6 times 5 is negative 30. Well, we have a negative second derivative. So the graph is concave up if the second derivative is greater than 0. So this would be for values that are less than 0. Now notice back here again at this definition. Here, it has to be concave up or down on I, which is an open interval. So when we are doing concavity, by definition, we will not include these points here. So with the first derivative, when we're saying where it's increasing and decreasing, we will have equal to symbols here, because we can include these points. By definition, concavity, we will not include the inflection point as a place where it's concave up. And concave down where it's negative. So, and if we wanted to use the inequality symbols, concave up, x values less than 0, concave down, x values greater than 0. And let's look at one last example. Find the intervals in which the function f of x equals x squared ln x is increasing, decreasing, concave up, so on. So let's take the first derivative. This is a product rule here, so first term times the derivative of the second term plus the second term times the derivative of the first term. And just tidying it up here, x plus 2x ln x for the first derivative. The second derivative then would be the derivative of this. Derivative of x is 1. We have another product rule here. So first term times the derivative of the second term plus the second term times the derivative of the first term. And we would get 1 plus 2 plus 2 ln x, which is 3 plus 2 ln x. So we have our first and we have our second derivative. And now I need to find out where it's increasing or decreasing. So I'm going to find out first, where is this function slope equal to 0? So here's the derivative. Where is it equal to 0? And I can factor out x in this question. And I would get x equals 0 here, or the other factor, -1, gives me ln x equals -1/2, and solving for x, remember ln is log base e, so using the back rule here, x equals e to the -1/2. So these are the places where the first derivative is 0. So I'm going to plot this here. There's 0. Here's e to the -1/2. And I'm going to test my 3 regions. So going back into this one here, I'm going to try, let's call this region 1, region 2, region 3. Try a number like -10. That would clearly be negative. We can't take the log of -10. In fact, we can't take the log of anything negative. So this function is not defined for any values less than 0. Let's test the region between 0 and this number here. Well, if you went and figured out approximately what this is as a decimal, e to the 1/2 means the square root of e, and then it's reciprocal. So I'm going to try a really small number. I'm going to try a number like 0.1. If I tried a number like 0.1, this would be positive. The log of 0.1 is negative, and I'll work this out in a calculator here separately and let you know what it is. And the answer definitely turned out negative. So this area here is going to be a place where the first derivative is less than 0. And then I'm going to test a point in this region here, like 10. ln 10 is positive, times 2 is positive, plus 1 is still positive, times 10. This would be a positive region. So this function is decreasing on the interval from 0 to e to the -1/2. And I used a round bracket here because the function is not defined at 0. If you look back at the original function, ln x, x has to be greater than 0 for it to be defined in the first place. So decreasing on that interval, increasing on the interval from e to the -1/2 to positive infinity. Now we're going back and looking at concavity. So let's find out the inflection point where it's located. This is our second derivative, and we need to set it equal to 0. So 2 ln x equals -3, and divide by 2 is -3/2. So x equals e to the -3/2 is the location of our inflection point. And we could find out what the y value would be simply by substituting it in here. But the question just asked for the location of the inflection point, so this is where it's located, just the x value. And now I need to test its concavity, so e to the -3/2. And that gives us 2 regions where the concavity will be either positive or negative. And I'm going to test a number somewhere between 0 and e, because again our function is not defined for x values less than 0. And I'm going to test a number on the calculator here. I'm testing a number on the calculator between 0 and e to the -3/2. When I substituted into this function, it was negative. And now testing a number that is greater than e to the -3/2, such as 10. is going to give me clearly a positive value here when I substitute it in. So this graph is concave up on this interval here, so from e to the -3/2 to infinity, and it is concave down where the second derivative is negative, and that's on this interval here. So increasing, first derivative greater than 0, decreasing, first derivative less than 0, inflection point where the second derivative is equal to 0, concave up where the second derivative is positive, greater than 0, concave down where the second derivative is less than 0.